this set of notes, we're going to talk about tangent planes and differentiability. So when we first encountered differentiation of functions of a single variable, we were able to show that the derivative had a geometric interpretation. And so what we saw previously is if the function is drawn here in red, then the tangent line would be that line in blue. And so what that did was that helped us look at different rates of change across the function. And we can actually extend this idea to multivariate functions. And in particular, we're going to talk about what the geometric interpretation is of that derivative when we're working with a function of two independent variables. And so when we're working with a function of two independent variables, we've seen previously that we could make a surface plot. And so here in the picture down below, we have in blue, we have the surface plot. And then kind of in this brown tan color, we have a tangent plane. So originally, we would have a tangent line. So it makes sense that if we're going to add on a new independent variable or a second independent variable, then also when we think about the geometric interpretation of the derivative, that is also going to expand by one dimension. And so now instead of a line, we're going to have a plane. And so it's very similar. We can see that this plane, if we were to evaluate the derivative at a single point, and here we would have the point P, we could see that that tangent line is going to touch that surface at the point P. Very similar to when we looked at a tangent line. And so we can find the equation for a tangent plane. And so listed here, we have what that equation would be. And so if the tangent plane to the surface, and so first we have our function here, so we have that z is equal to f of xy, so x and y here are going to be my two independent variables, and if we want to evaluate that at the point xyz, and notice that this point exists in 3 space, so that's why we have to evaluate it at a point xyz, similar to earlier when we would evaluate at a single point, we would have the point xy. We can say it exists, and the tangent plane has the following equation. And so looking at this equation, notice here, here, and here, this is where the point that we're evaluating the derivative at or finding that tangent plane surface at is. And then also we're going to need to find some of those partial derivatives. So we have the partial derivative of the function with respect to x and the partial derivative with respect to y. And since we are trying to find the equation for the tangent line, we're not going to substitute anything in for the y, the x, and the z. So this is very similar to when we would find the tangent line that we looked at several chapters ago. So let's look at some examples to see how we could find the tangent plane at an indicated point. All right, so starting here with this example. So we want to find the equation of a tangent line at the indicated point when we have this function. So the first thing that we're going to note is that the point 1, 2, negative 11 is contained on the surface. And what we mean by the surface here is we mean the surface created by this function. So z is equal to x squared minus 3y squared. And we know that this point is contained on that surface because if we evaluate this function, so we have 1 squared minus 3 times 2 squared, that's equal to 1 minus 12, which is equal to negative 11. And you can see here we have the negative 11 for the z. So we know that this point is on that surface. So to find the tangent plane, we need to calculate those two partial derivatives. So let's start out by calculating the partial derivative with respect to x first. So looking at my function up here, notice that only the first term actually contains an x, so the second term will just be treated as a constant. So if we take the derivative of x squared with respect to x, we get 2x. And then of course the second term, minus 3y squared, doesn't contain an x, it's a constant, so the derivative of that term with respect to x is just 0. We could also find the partial derivative of f with respect to y. So very similar, the first term, x squared, doesn't contain a y, so it's a constant. So the derivative of x squared with respect to y is just going to be 0. And then our second term, negative 3y squared, the derivative of that term with respect to y is going to be negative 6y. Next, we need to evaluate the partial derivatives at the point x naught, y naught. So where does this point come from? Well, first, if we go back up to our function, notice in our partial derivatives, we are evaluating them at x naught, y naught. And so x naught, y naught is just going to be the first two points from that point on the surface that we are interested in. So in this case, our x naught, y naught, since we're interested in the point 1, 2, negative 11, we're going to evaluate at the point 1, 2. So the partial derivative of the partial derivative of f with respect to x at the point 1, 2 is equal to just 2 times 1, which is equal to 2. Notice here we don't do anything with the y term because y is not in this partial derivative. But as we have seen, there are cases where y could be in there, so that's why we do have both points there. And then we're also going to evaluate the partial derivative with respect to y at the point 1, 2. And notice here that's going to be equal to negative 6 times 2, or negative 12. And then finally, we'll be able to write out what that equation of the tangent plane is. And so we're going to be using the formula here in this box. And so on the left-hand side of the equation, I'm going to have z minus z naught. So notice z naught here was negative 11. So I'm going to have z minus negative 11 is equal to, and so my next term, I'm going to have that partial derivative with respect to x evaluated at the point times x minus x naught. And so that is going to be 2 times x minus 1. And then I'm going to do something very similar for the partial derivative with respect to y. So the partial derivative with respect to y evaluated at the point x naught, y naught is negative 12. And I'm going to multiply that by y minus 2. And then we could go through here and simplify, and if you'll do that, you'll find this is equal to z equal to 2x minus 2y plus 10, and that gives the equation of the tangent plane. So we might want to discuss the conditions under which the tangent plane exists. And so in order to do that, we need to define what it means for a function of two variables to be differentiable. So previously, we did look at functions of two variables, but when we talked about the derivative, we mainly just talked about the partial derivatives. And so remember, what a partial derivative does for us is it lets us look at that rate of change, or how the function is changing, if we only change one of the variables. Here we're giving a not partial definition or a partial derivative, we're actually giving a full definition of differentiability for that function of two independent variables. And so here we suppose that f of xy is a function of two independent variables and that both the partial derivatives are defined throughout an open disk. And so remember, we talked about an open disk as being the analog to an open interval, but instead of being on a line, we're now in a plane, but it's a very similar idea. And so if you'll notice, what we have here, this equation right here, is very similar to that equation of the tangent plane that we just saw. We have that partial derivative at the point x minus x naught, the partial derivative with respect to y, also evaluated at that point times y minus y naught. And then here you've got f of x naught y naught, and so that's going to be similar to the z that you saw earlier. So what we have here is if the limit of this piece, the limit of the difference of this piece from the actual function, and then here we're going to divide by this piece. As that limit goes to 0, or if that limit goes to 0, then we're going to be able to say that the function is differentiable. And so this all relates back to the idea of the tangent plane. So without getting too far into the details, essentially what we're doing is very similar to what we did with the tangent line, except instead of looking at the limit along that line, we're now looking at the limit across the plane. And so the key idea in both the one and the two-dimensional case is to approximate functions by a linear function, which we haven't covered in detail in this course, so that the error in the approximation vanishes as we approach the point to which we approximated the function. So remember that, again, if we looked at that tangent line, we were approaching the point along the line. Here, same idea, we're just approaching that point across the plane. And so as in the one-dimensional case, we have the following theorem that if f of xy is differentiable at a point, then it is going to be continuous at that point. But remember that that reverse may not hold. Just because a function is continuous doesn't necessarily mean that it's differentiable. Now we do have a sufficient condition for differentiability which states the following. Suppose that f of xy is defined on an open disk centered at x naught y naught, and we have the partial derivatives. So if we have f of x defined on that open disk and the partial derivative exists and are continuous on that open disk, then f of xy is differentiable. All right, so let's look at an example. We're going to show that f of xy is differentiable at the indicated point. We can use the sufficient condition for differentiability to help us out with this exercise. So, to apply the sufficient condition for differentiality, we need to have the partial derivatives. So let's first find the two partial derivatives. So we're going to find the partial derivative of f with respect to x first. So looking here, the first term is xy, y is a constant, so here we're just going to have y for the first term, plus 3x squared, so the derivative of that term is 6x. Then we can find the partial derivative of f with respect to y. The first term xy, this time x will be a constant, so we just have y. And the second term doesn't involve y, so the derivative of that term with respect to y will just be 0. All right, so next, if we're going to apply that sufficient condition for differentiability, we need that f of xy is defined on an open disk centered at x naught y naught. So notice here, there's no reason for f of xy not to be defined on an open disk centered at the point 1, 0. This function is defined everywhere. Next, we need those partial derivatives to be continuous on that open disk centered at x naught y naught, so in other words 1, 0. Well, these are both polynomials. We know that they are both differentiable and therefore continuous, so everything is fine there. So therefore f of xy is going to be differentiable at that point 1, 0. So here we could say that both are polynomials. and differentiable everywhere. Therefore, both are continuous on an open disk centered at 1, 0. And again here, since they're continuous everywhere, they're polynomials, then it's not just at 1, 0. We could really have had any point here. And then also f of xy is defined on an open disk centered at 1, 0. And again, this is because this function is defined everywhere, so we don't have to worry about it. And then therefore, f of xy is differentiable at x naught, y naught. And so what this means is we can define a tangent plane at the point 1, 0. And so we could do that very similar to what we did on page 2 of the notes. All right, so the last thing we're going to talk about are vector-valued functions. So far we've only considered functions which take in real numbers and return a single number. We can also consider functions whose output is a set of numbers, more specifically a vector. And so such functions are known as vector-valued functions. And here's a little bit of that notation. So we're saying that function is a map from a set of real numbers to another set of real numbers, and they don't have to be equal in terms of dimension. And so this is another way we could write this. So we're going to take n outputs, and then we're going to get we're going to take n inputs and get m outputs. So in other words, there are m rows to this vector. So there's other ways that we could write this notation. Your book will use something like this when we have just 2 inputs. Or maybe something like this. And so you'll see both of these. So let's look at some examples, and I think once we look at some examples, this will make a little bit more sense. So here we're going to have a couple examples of functions, and we're going to evaluate those functions at different given points. So the first function we have here is f of xy is equal to the vector where the first term is 2x minus 3y, and the second term is 4x squared. And so notice here, this isn't a step function. We're not saying we use 2x minus 3y in one condition and 4x squared doing another one. We're actually going to evaluate both of these. So if we want to evaluate this at the point 1, 2, this would look like the following. So what we're going to have here is the function evaluated at 1, 2 is equal to, and our first term is going to be 2 times 1 minus 3 times 2, and then the second term is going to be 4 times 1 squared. And so we get negative 4 and 4. Here's another example. Now before we actually evaluate this one, let's practice some of this additional notation, other ways that we could write this function. So we could write the function this way. Another way your book will write this function is the following. And so if we write it this way, corresponding with the top alternative way here, the f of xy would be the natural log of x plus y, and the g of xy would be the e to the x plus y. Or using this formulation right here, we would say that u is equal to the natural log of x plus y, and v is equal to e to the x plus y. All right, so let's evaluate this function. So again, we're going to evaluate at the point 1, 2. And so we would have the natural log of 1 plus 2 e to the power of 1 plus 2, which is equal to the natural log of 3 e to the 3. So very similar to what you've seen before, it's just now instead of having a single number as the output, we have two numbers of the output. And you can extend this all sorts of ways. And so, for example, kind of down here, we could write one that looks like this. So it could be the same thing that we've got above, but we could also have a third function. And so, for example, we could have x plus 2y. And so notice the output here would be the natural log of 3, e to the 3, and then we'd have 1 plus 2 times 2, which is 5. So this idea, when we have a function that maps to a vector instead of a single number, we can still look at partial derivatives, but we have to treat them a little bit differently. And in order to do that, we need to talk about the Jacobian matrix. So a Jacobian matrix is a matrix composed of first-order partial derivatives of a multivariable function. And so your book focuses on using the Jacobian matrix for linearization. In BST 675, you'll find that the Jacobian determinant is useful in determining a change between variables. And you'll see that more in that course. So for right now, I just want to focus on how to compute a Jacobian matrix. And so in general, if we have a function that has n inputs and m outputs, this is what the Jacobian matrix would look like. And so essentially what it's doing is in this first row, what we're going to do is for the first function that's listed, you'll take the partial derivative with respect to all the variables. And then you'll have the second derivative, and you'll take the partial derivative with respect to all the variables, and so on. And so we're going to look at some examples of this so you can see what it looks like. Your book focuses on the case where n and m are both equal to 2. So in other words, like these examples that we just saw, you've got 2 inputs and 2 outputs. All right, so we're going to look at those functions that we saw earlier, and we're going to see how we could write the Jacobian. So one way to think of this is we have the first function, and we have the second function. And then we've got our two variables. So x is the first variable, and y is the second variable. So when we go to write the Jacobian, what we're going to do is we're going to start with the first function, and we're going to take the partial derivatives with respect to each of the variables. So our first function is 2x minus 3y. So we first take the partial derivative with respect to x, and that's just going to be 2. And then we take the partial derivative with respect to y, and that's going to be negative 3. And then we jump down to the next row. And so in the next row, we're going to look at the second function. We take the partial derivative with respect to x, which is going to be 8x. And then we take the partial derivative with respect to y, and that's going to be 0. So notice, however many functions you have in your output, that's how many rows you're going to have. And however many variables you have is going to be the number of columns in the Jacobian. So therefore, the number of rows in the Jacobian is determined by the number of functions, and the number of columns is determined by the number of variables. So let's look at one more example. So notice here we've got 2 functions and 2 variables. So we know our Jacobian is again going to be a 2 by 2 matrix. All right, so our first function is the natural log of x plus y. So we're first going to take the derivative of the natural log of x plus y with respect to x. So we're going to use the chain rule to do this. So we know it's going to be equal to 1 over the inner function, which is x plus y, times the derivative with respect of the inner function, which is just going to be 1 in this case, so we're just left with 1 divided by x plus y. Next, we're going to take the partial derivative of the natural log of x plus y with respect to y this time. And again, by the chain rule, we're going to have 1 over x plus y, now times the derivative of the inner function x plus y with respect to y, which again is just 1. Looking at the bottom function. So our bottom function is e to the x plus y. Well, if we take the partial derivative of that with respect to x, we end up with e to the x plus y. And the partial derivative of e to the x plus y with respect to y is also e to the x plus y. So that is how you compute a Jacobian. And like I said, for right now, we're not really going to do anything with the Jacobian, but you do need to know how to compute those for the future. So moving forward, this course has provided a foundation for the calculus skills that you'll need in the MSBST program. It is not to say that this course has provided all mathematical content that you might need. There are going to be times in your courses that you'll need to learn some new mathematical concepts on your own. So this course was really designed to provide you with the skills so that you can learn the additional skills on your own. So for example, the course has not covered integration of functions with 2 or more independent variables, but extending what you've learned about integration of functions with a single independent variable and what you've learned about functions with 2 or more independent variables, this is going to make learning about integration of functions with 2 or more independent variables very straightforward. So you now have all of the foundational information that you need, but just keep in mind as you move forward, there may be some new skills that you need to learn on your own, but you do have all the foundations you need to be able to do that. So as always, if you have any questions over this video, please let me know.